Digital data has a literal physical footprint. If you take just 1 second of uncompressed high-definition video and break it down into its raw components, it occupies more than 20 megabytes of space. Audio is no different. A vintage CD player like this illustrates the foundational scale of the problem. Even a simple 2-minute uncompressed track is a massive data burden for standard storage. This creates a structural conflict. The digital revolution, streaming video, the mobile internet, wireless calls, is mathematically incompatible with the sheer size of raw, uncompressed information. Without a way to shrink these files, our bandwidth would fail. As more data is pushed through the network, the infrastructure eventually stalls and turns rigid under the pressure of the payload. The solution is data compression. This discipline is built entirely on a single observation: that information in our universe tends to be redundant, with patterns that repeat and recycle. Compression is not just a background utility, it is the structural framework that allows the modern network to function without collapsing under its own weight. The first approach is lossless compression. This method requires bit-for-bit perfection. It is the mandatory standard for text, bank records, and medical files, where a single missing character or missing pixel is a total failure. This logic traces back to the 19th century. Samuel Morse, pictured here, realized that human language contains predictable mathematical patterns. Morse knew E appears constantly, Q is rare. Giving E a dot and Q a complex sequence of dashes reduced transmission time. Computers use this logic through Huffman coding, assigning shortest binary strings to frequent data, minimizing ones and zeros. Other systems, like LZW, look for even larger repeating blocks. This is the method that powers GIFs and the original file structures of the Unix operating system. LZW works by building a dictionary of repeating patterns. If it identifies the word "the" or a specific block of blue pixels, it records that pattern on an index card. From then on, it only sends that index number, replacing the original data and shrinking the file to a fraction of its size. By acting as a perfect mathematical organizer, lossless compression reduces the size of a file without losing a single piece of the original information. But there is a limit. You can only reorganize a file so much before you run out of patterns to exploit. Claude Shannon, pictured here, was a mathematician who proved that a hard, theoretical stopping point exists. He called it entropy. It is the mathematical wall where all redundancy has been removed. At this point, the data is purely random, and it cannot be shrunk any further. If Shannon's floor is the absolute limit for perfect data, lossless compression alone cannot explain how we stream 4K movies through the air today. To move past Shannon's limit, engineers shifted their strategy. They stopped trying to achieve a perfect bit-for-bit reconstruction of the data. This is lossy compression. If the file doesn't need to be perfect, can it still be close enough to fool a human? Using techniques like quantization, engineers take the original analog signal and strip away specific information that our senses are too limited to detect. This waveform shows the trade-off. By slicing off high-frequency audio only dogs can hear, or deleting color shifts too subtle for the human eye to see, the data counter plummets. We lose the data, but we keep the experience. Lossy compression succeeds by accounting for our biological limits. It removes parts of reality that we would never have noticed in the first place. Modern data compression is a two-pronged attack on inefficiency. It represents the marriage of cold mathematical probability and a masterful manipulation of human biological flaws. Every web page you load or video you stream depends on this process. Communication tools from this early cellular brick phone to modern 5G networks are built on these algorithms. It means that in the digital world, we are rarely looking at the whole picture. Watch this complex object collapse into a framework of glowing points. It maintains its shape, but the core is gone. The digital world is a perfectly pruned mathematical illusion, using the absolute minimum data required to convince our brains that it's real.